Hello everybody. Today we're going to talk about um, the content for Lab 8, which is how to accurately determine protein concentration using a Bradford assay. So again, after this lab, you should be able to select a quantification method based on the protein sample composition, calculate the specific activity and fold purification step. So these are the two values that you're going to be adding on to your purification table, and specifically, these are the values that are going to allow you to determine how effective a particular step is. You need to be able to explain the trends in total activity, specific activity, and fold purification as a protein purification process continues. And then finally, you need to be able to use a purification table to assess the quality of purification. All right, so let's talk a little bit more about the Bradford assay. Again, let's touch base because it's coming back and it's coming back with a vengeance. And we're going to be using it a little bit differently this time than we have in the past. So we use a Bradford assay when we have a protein that doesn't have any aromatic amino acids. So proteins that don't have any tryptophan, tyrosine, or phenylalanine, but specifically that don't have any tryptophans, because I think that tryptophans make up 99% of the absorbance of 280 nanometers. You use it when you have a sample that's not homogeneous. So you either don't know the purity of the sample, or it's an intentional mix of proteins. So like a cell lysate. You can't use an A280 with cell lysate because there are all these different proteins that have different instantiation coefficients in there that you can't account for. And then finally, some proteins just don't behave well with the absorbance at 280 assay. And so in that case, you would use a Bradford assay. So if we recall, the way the Bradford assay works is when we have our Bradford reagent here, we have it on its own, it's brown, and it does not absorb at 595 nanometers. However, when the Bradford reagent binds the protein, again, this is not to scale, the color changes and we see it turn blue and it absorbs at 595 nanometers. And then over a given range, the relationship between A at 595 and concentration is linearly proportional. And it's really important for accurately quantifying protein concentration that we are in that area of linear relationship. So the principle of the Bradford hasn't changed from when we used it in labs 4 and 5. What's different this time is that we're going to be more careful in quantifying our protein concentration. So the last time we did the micro well plates and we let the Bradford assay and the protein sit for like 2 hours, and if our absorbances for our samples were outside of the calibration curve, we didn't really care. Things are going to change this time. And so instead of a microplate, we're going to be running 1 ml assays. And instead of adding 5 microliters of sample, we're going to be adding 50 microliters of sample. So you're going to create your standard curve by looking at BSA standards in a cuvette one by one. There's also, you need to let the reagent react with the protein, and that's between 5 minutes to 1 hour. So before, you let your Bradford and your protein sit there for like 2 hours. In this case, if you want an accurate result, you can't let your sample sit for more than an hour before you read it after you add the Bradford. And then the other big distinction is that your assay must be linear. And in fact, you need at least 4 points in that linear range. And that's because when you're out of that linear range, the BSA curve is going to start, the BSA line is going to start curving. And so we look down at this calibration curve over here, you can see it's nice and linear. But what can happen is after we access that top point, they might start flattening out. and because eventually it's going to flatten out and stop being linear. So if you have a protein, so in this case, what happens if a sample is more concentrated than our highest standard? So let's say you have a standard that gives off an absorbance of 1.3. In theory, you might think, oh, I can just extend that line. Oops, let's bring this back. It's fine. I can just extend that line. And 1.3, that's going to correspond to like 7 micrograms. Fine. No, that's not the case. Because if you look here, one possibility that can happen is your curve can flatten out. And then it turns out that your protein isn't actually 7 micrograms, it's somewhere over here. And so that's why we need to make sure that our sample is linear. And you'll see this when you're graphing your standards. Some of your higher concentrations might be flattening out, and you have to throw out those points, and you can't measure past your top point. So what happens? So again, the only range that we can accurately quantify is within the highest linear standard, the highest end of the linear standards down to the 0 point. Ideally, you would be between your lowest concentration, that's not 0, and your highest concentration, that's within the linear range. So you're going to be going through your samples, and you may decide that you're going to add a particular amount of your BSA particular amount of your pooled samples, and you're inevitably going to run into a situation where you're going to get an absorbance that's higher than your highest standard, your highest BSA standard. If this happens, stop. Don't keep going, and don't give me attitude if you go all the way through and half of your samples are above the highest concentration, because you have to go back then and you have to adjust your sample so it's within the linear range. So there are 2 options that you have, or a combination of these 2 options that you can use to fix your sample to give it a lower concentration or a lower absorbance, and then you can back calculate. The first is you can add less sample. So you're adding a total volume of 50 microliters to your cuvette. So you can add less protein and more BSA and more water. That's one option. The other option is you can dilute the sample, then add the same amount. Or you can dilute your sample and then add a different amount of that diluted sample. That's up to you. That's why you keep a lab notebook, so you can keep track of all these numbers so you can get accurate results. And then there's the issue of what happens if a sample is less concentrated than the lowest standard. So let's say you get a value that comes in around over here. Again, we want to be between this guy and the top guy. And so at that point, what I would recommend doing is adding more sample. So you don't want to dilute it, but let's say you're adding 25 microliters of protein and 25 microliters of water. Why don't you try adding 50 microliters of protein? So play around with the amount of protein that you add, and that to either bump you up or down into the linear range. And again, this is really, it's of utmost and key importance. Can't emphasize this enough because several people did this last term. You need to make sure that when you're looking at these results that you're in the linear range, and then if not, adjust accordingly. Okay, so I've talked a lot about diluting and changing the amount that you add. So let's see how this would play out for an actual concentration. Okay, you have 20 microliters of 50-fold dilution of sample to 1 ml of Bradford reagent, and you get an absorbance of 0.522. The standard curve is shown on the previous page. What is the concentration in mg per ml of the original sample? Okay, so the first thing we do is we solve for micrograms of sample. And we do that by taking the calibration curve up here. So y equals 0.1999x plus 0.0021. Okay, so we know the y and we're solving for x. So 0.522 equals 0.199x 9 plus 0.0021. Let's grab the calculator here because I don't have a calculator in my head, unfortunately, at least not as good of one as I would like. All right, so 0.5199 equals 0.1999x. Okay, so x is equal to 2.6 micrograms. Okay, so now we have micrograms of sample. So then the next is we find the concentration of sample that we added to the cuvette. And so we do that by taking the micrograms in the cuvette and dividing it by the microliters added. And we don't want to mess with the dilution that occurs when we add our sample to the water. So what we do here then is just we would say, okay, we have 2.6 micrograms of protein, and we added 20 microliters of our sample of our 50-fold dilution sample to the cuvette. So we divide that by 20 microliters, and so that would give us 0.13 micrograms per microliter. And if we were to convert microliters to milliliters and micrograms to milligrams, you would see that the top and the bottom cancel out. And you get 0.13 mgs per mil. Okay, that's the sample of our diluted guy. But now we have to go back and we have to account for the 50-fold dilution. So what we do is we need to get the concentrated sample. So if we have 0.13 mgs per mil, and that's our 1x, or our final concentration, what would a solution, 50. And our original sample is 50 times as concentrated. What would the concentration of the 50-fold concentrated stock be? And so that would turn out to be, 0.13 mgs per mil times 1 is equal to 50-fold times X concentration. So that would be equal to 0.13 times 50. And that would be 6.5 milligrams per mil. And that's our stock concentration. And so kind of the short way we can do that is we can say, okay, I'll put this in another color. We could take the micrograms of protein divided by the microliters added, the microliters of sample added to the cuvette, and then multiply that by the dilution factor if you have a dilution factor, and you're not always going to have a dilution factor. And I would argue in most cases, you're probably not going to have a sample that's concentrated enough that you're going to need to dilute it ahead of time. But either way, that is the calculation. So that's the micrograms of protein that you calculate from the Bradford. That's the microliters of sample that you added to cuvette. So you're not including the water there. And then finally, if you have a dilution factor, you would multiply it by the dilution factor to calculate back to what the original sample concentration is. Okay, so then there's a really, so one of the things that you can do to determine if your sample is too concentrated right off the bat, because again, you're going to want to be keeping an eye on this to make sure you don't have to go back and redo your calculations, and that's to look at But the question is, it's going to be, it's going to take a lot of time before you can actually put your sample into the cuvette and then see whether or not the absorbance is higher than the standards. And so one of the ways you can keep up and keep track and make sure you don't have a bunch of samples that are too concentrated, so you have to redo the whole thing, is to visually inspect. And you guys are doing this all along when you're monitoring the intensity of the blue. If one sample is bluer than your highest linear, than your higher linear BSA standard, if it's obviously bluer, even if it's close, don't wait around to read it. Just go ahead and dilute that guy down, because if it's looking like the highest standard, it's going to be the highest at the higher end of your curve anyway, and it's going to be better for you to dilute it down so it's at the middle or near the bottom, so you can use it. So be vigilant, watch that blue intensity, and trust your eyes. Okay, so you guys are going to be generating a lot of new data in this lab. And so I'm going to recommend that you make a new table in your lab notebook to keep track of all these new data that you're acquiring. Okay, and so in this case, I recommend you set up a table here so you have your sample, and for each sample, you're going to want to use the volume used. So the volume, and then this can even be a two-part column here, where you'll use the volume of the protein and then the volume of the water. And again, this is the volume that we're going to divide by to get the concentration. Then you're going to keep track of your dilution factor if you have it. You're going to record the absorbance at A595. And then for the micrograms of protein in dilute solution, that's where you're going to plug in the values from your calibration curve. And then finally, the micrograms per microliter, that's going to be column 2 divided by, that's 1, 2, 3, 4, 5. That would be 6. That would be column, erase here. That would be column 6 divided by column 2 multiplied by column 4. If you used a dilution factor, otherwise column 4 would just be equal to 1. All right. And so then you're going to take some of the information from this table, you're going to modify it, and then you're going to plug it into your big purification table. Okay, so I made a big deal about why we need to know how many milligrams of protein is in a sample. You may be wondering, why does that matter? And that's because we need it to assess the quality of our purification, because we needed to use to calculate the specific activity. So if we look at our samples, let's say LDH is the purple guy, the purple protein here, and we're going to visually count the number of each type of protein that we retain throughout the purification process. So in our lysate, we have 1, 2, 3. We have 3 units of LDH. However, we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 16. We have 16 total proteins, or 16, milligrams of protein in that sample. And if we were to divide the units of LDH by the total mgs of protein, we would get specific activity, or a units per mg as 0.1875. As we go to post-IEX, okay, we see we've still retained those 3 LDH proteins, but we've lost some of the other junk. So we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. 3 divided by 11, 0.27. So our amount of LDH has stayed the same, but the total amount of protein we have has gone down. And so our specific activity, which is the relative ratio of how much LDH we have based on all the proteins in our sample, is going up. And so ideally, our units per meg would be a big number. And the amount of LDH would be big relative to the rest of the sample. In this case, by the way we're counting here, we would be looking for a value of 1. Okay, so let's see what happens when we go to our affinity column. So our milligrams of protein have gone down here, so we only have 2. So we have 2 LDHs, but we have a total of 1, 2, 3, 4 proteins. So we see a units per milligram of 0.5, and that's our highest fraction there. So we can use this value of specific activity, or the units of LDH divided by the total milligrams of protein, and that tells us how much of our protein is LDH. How much of our protein is LDH? Because ideally, the amount of total protein will go down and the amount of LDH will stay constant. So what a good purification is going to look like is, again, the specific activity is going to increase throughout the purification. And in fact, after your last step, you're going to hope that it's going to increase by several orders of magnitude. And again, ideally, your total protein is going to decrease, but your amount of LDH is going to stay constant. Now, what really happens over the process of the amount of your total protein may go down, but the ratio of LDH to total protein will increase, and ideally, this would be equal to 1 because you want all of your protein to be LDH. In an ideal world, that's what we would see. What really happens, if you know from doing your purifications, that when you have your peak of your specific activity, so if we have the fraction number here, and we have the LDH activity, and you have a peak, ideally, you want to say ideally, so all these fractions have LDH, and even like fractions like this guy through this guy have a decent amount of LDH. However, you're only allowed to take like 2 or 3 fractions during those purification processes. So you leave some LDH behind in every purification. So your total amount of LDH in milligrams is going to go down. But also, there are going to be contaminating proteins there probably. And that's why we don't take all the fractions on the edges, because you want to minimize the other proteins being taken up. So in reality, you're probably going to see the specific activity, it's going to increase. However, the amount of LDH is going to go down throughout the purification, and there's a good chance that your total protein is going to go down a lot too. And also, with the LDH going down, you're going to see that manifested, and the total activity is going to go down. You would ideally want this activity value to stay constant, so you're having the same amount of LDH in every single sample. However, because of these reasons we talked about, you're going to lose a little bit, and sometimes even a lot, of LDH at each step of the purification. And that's just like, again, it's the struggle between yield and purity, the constant struggle of a biochemist. Okay, so I've been talking about these new calculations, and now I'm going to show you how they fit into the purification table. So the new guys that we're going to be doing today are the total protein in milligrams, specific activity, and the fold purification. So the total protein, you're also going to plug in the protein concentration in milligrams per mil. You already know how to do that calculation. You're just filling it in more accurately this time. So with the total protein, you're literally taking the mgs per mil, and you're multiplying it by the mils of sample. And that's giving us the total protein in milligrams. Okay, so for the 40%, this would be 5.4 times 141. And feel free to stop me at any point to try this on your own. I highly encourage you to do so. Equals 653.4 milligrams. Oops. 141 times 5.4. Let's try that again. Stupid iPhone calculator. 761.4 milligrams. Now for the affinity, that would be 2 moles times 0.54 1.02 mgs. So again, we're seeing that the total protein is dropping, and that's not necessarily unheard of. That's not necessarily a bad thing if those 760 milligrams that you're getting rid of are proteins other than LDH. And like I did mention here, you're going to see that it's just a fact of life that the total activity or a total amount of LDH is going to go down over the course of the purification, because you're always going to lose some of your sample at every step because no one is perfect. So next comes the specific activity. And again, the specific activity is important because the specific activity is going to tell us really the purity of our sample, because it tells us how much of our sample is actually LDH. And so again, the way that we calculate the specific activity is it's literally the units of LDH per milligram of total protein. So for the 40%, again, feel free to pause me. It would be total activity or units per mg. Okay. Units. So it'd be 698 units divided by 761.4 mgs, which would give us 0.917 units per meg. For the affinity, okay, so our total activity is 31.2. So yeah, that number's gone down. So again, I mentioned the activity. The decrease in time will also come from the total activity, because the total activity is the total amount of LDH in our sample. So yeah, that number is going down. So we did lose quite a bit of our sample along the way, which stinks. But again, that's a reality. 31.2 divided by 1.02 mgs, which gives us a value of 28.9. And so, like I mentioned here, the hallmark of a good purification is that specific activity is going to go up 2 or 3 units per milligram, or 2 to 3 orders of magnitude over the course of your purification. And you can see here from our 40% supernatant from the ammonium sulfate to the affinity pooled fractions, we're going up 3 orders of magnitude. So 3 orders of magnitude. So we're feeling pretty good about a 3 order of magnitude increase. But again, that may not be realistic for every purification. And then finally, the last step is this, as the last calculation is the fold purification. And this is an easy to see numerical indication of how effective the purification is. And that's literally the specific activity of a particular step divided by the specific activity of the original. So in this case, our fold purification, we're starting off with 40% supernatant. So our fold purification for supernatant is going to be 1, because that's what we're starting out with. But for the affinity pool, we would take 28.9 units per mg, because that's, again, the affinity divided by the specific activity of the starting step, which is 0.917 units per mg. 28.9 divided by 0.917. Okay, and that gives us a fold purification of 31.5. All right, and so if you're seeing double digits in your fold purification for your last step, you're in good shape. So yes, so one of the weaknesses of this particular purification is that you're losing a lot of LDH. So we're talking, we end up with a total activity of 31.2 units versus almost 700 units starting off. So we did lose a lot of protein, which kind of stinks. However, our specific activity, we're going up 2 to 3 orders of magnitude, which is good. And then our fold purification, our sample is 31.5 times more purified or more pure than it was at the beginning when it was in the cell lysate. So the fact that we have such a high change in our specific activity, and then we have a 32% fold purification, a 32-fold purification, means that even though we didn't retain a lot of sample, that means our sample is pretty darn pure. And so we're happy about this, and we can move on with our lives. We can use the next lab is going to tell us visually whether or not this fold purification will tell us whether or not there are actually other proteins that are in there that we can't see in the fold purification. But for now, by the math, we're pretty happy. So the next calculation that I've got to talk about, and this is a complicated calculation. This is something you're going to get stuck up on. That's okay. We're going to go over it again in class, and you can come talk to me at office hours. And this is the conversion from Vmax to Kcat. So in theory, we understand the difference between Vmax and Kcat, and we understand that Kcat is advantageous because it takes out the enzyme concentration component. So Vmax is equal to Kcat times the total enzyme concentration, or Kcat is equal to Vmax divided by ET. So we're getting rid of that enzyme concentration. But then the quick question is, okay, how are we going to calculate the Kcat? Okay, and so in layman's terms, what you have to do to figure out the Vmax is you have to calculate the Vmax, and you're going to calculate the Vmax from, this is the Vmax you're going to get from your Michaelis-Menten lab, and remember that's the affinity sample. And then you have to divide it by the micromoles of enzyme. And you're going to get the micromoles of enzyme from the milligram per milliliter concentration of your affinity pool. So this is going to be coming from this lab. And then your Vmax, you're going to be pulling from lab 6. So you're going to be pulling, and again, this is why we harangue you, one of the many reasons why we harangue you throughout the semester to keep a good lab notebook, because you have to go back and you have to pull out your Vmax from that lab. All right? Okay, so let's tackle this problem in terms of actual calculations. So kinetic assays were performed with different concentrations of NAD using a 1 ml cocktail solution, 25 mL, 10-fold dilution of a 0.61 mg per ml enzyme sample. Okay, we have the Vmax, 0.51 micromoles of NADH per minute. Okay, so this is going to be our top component. So this is going to be our Vmax. Then the question is, how do we figure out how much enzyme we added? Okay, and then also, yeah, the micromole of enzyme is coming from lab 8, but you also need to take your dilution from lab 6. as well. So this is why this calculation trips a lot of people up. It's because you have to pull from a lot of different labs, and that's okay. All right, so let's get started on tackling this. So we have a concentration. So we know that our concentration of enzyme is 0.61 mg per mil. So we used our Bradford assay, and we determined that our stock affinity pool is 0.61 milligrams per milliliter. Okay? So if we take our stock here, so this is our stock. This is 0.61 mg per mil. But we didn't stop there because you had to go back, because if you were to add this enzyme straight into the cuvette, it would like max out in a minute. So you went ahead and you did a 10-fold dilution. And then you took 25 microliters of that 10-fold dilution and added it to the enzyme cuvette. Okay. So what we do then is we have to go ahead and we have to figure out, okay, so we know that we have 0.61 milligrams per mil. That's our sample. So we want to figure out what's the mg per mil concentration of the dilution that we added to the Eppendorf tube that then got put into the cuvette. And so we take the concentration of the stock and we divide it by the dilution factor, which in this case is a dilution factor of 10. And then we divide it by the microliters added to the cuvette, or the milliliters added to the cuvette. So this would be 0.61 mg per mil divided by 10 times 0.01 or 0.025 mils. And so that's going to give us 0.001525 milligrams. So now we know how many milligrams of enzyme are going into the cuvette. So now that we have the milligrams, we have to convert milligrams into micromoles. And so if we have 0.001525 milligrams times 1,000 milligrams per gram times divided by the molecular weight of LDH, because again, we're doing this per monomer. So LDH is a tetramer, but each monomer catalyzes a reaction. Sorry, that's a bit of an aside. So 37,500 grams per mole. So that gives us the moles. Then we have to convert to micromoles. So again, we put the moles on the bottom. We multiply by 1 times 10 to the 6th micromole, because there's 1 times 10 to the 6th micromoles per mole. And that's going to give us 4.1 times 10 to the negative 5. Whoops, let's erase that. Whoops. Now everybody gets to see the quilting fabric I was looking at. All right, times 10 to the negative 5 micromoles. Okay, so now we're going to have to go and move this calculation down here. All right, go away, Camtasia. Oh, okay. And so what we have to do then is, again, we need to take the Vmax of the reaction in micromoles per minute, and then we divide it by the micromole of enzyme. So our Vmax we already determined is 0.51 micromoles per minute. And we divide that by 4.1 times 10 to the negative 5 micromoles of enzyme, and that's going to give us, let's go back and let's calculate. $12,439 per minute. So 12,000 per minute by 60, or about 210 per second. We divide that value by 60. All right. So again, comparing Vmax to Kcat. So we want to do, so we know how to get the Vmax, but to get the micromole of enzyme, we have to take the mg per mil concentration, and that comes from lab 8. We divide it by the microliters of enzyme added to the cuvette. And for this lab, or the milliliters, and for that list, got confused there. See, this is even a little confusing for me. We divide it by the dilution factor, and that comes from lab 6, and then we multiply by the milliliters added to cuvette, which you would go back and find from lab 6, but as I recall, is always 25 mils. And then that gives you a number of milligrams. Then you have to use milligrams, convert to grams, convert to moles, and then convert to micromoles. All right. Now, so that's, again, if you don't get this the first time, that's okay. Pause it, work through it on your own, ask me questions in lab. And then for this lab, you're going to be constructing a Bradford standard curve. You're going to be determining the milligrams of protein for each step of the LDH purification. You're going to complete the purification table and determine the total milligrams of protein, the specific activity of LDH for each step, and the Kcat of LDH. And then the pre-lab for next week is going to be a little bit different because you're going to be running an SDS page gel. So you're going to be visually assessing the purity of each sample using a gel. But for this lab, it's really important that you have the samples ready to go at the beginning of lab. So the pre-lab for this lab is going to be a little more complicated, and it's going to count for more points. Again, still a completion grade, but the homework is going to be due at 12, so I have more time to go through and get back to you. But I'll talk in a little more detail about the pre-lab assignment in class next week. All right. Anyway, have a great rest of your day, and if you have any questions, just send me an email.